Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration. Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Our pilots are constantly faced in flying into North Vietnam with missile firings.
We got things right under us.
For a long time, speed was the military aircraft designer's main objective. But in a dogfight, maneuverability is as important as speed. The fly-by-wire system and its computers provided a way to build potentially more maneuverable aircraft.
An urgent requirement to dramatically enhance air-to-air combat maneuverability, the program is called HIMAT. The main emphasis of the flight test program is high-G maneuvering in the transonic flight regime, where most fighter versus fighter combat occurs. Composite material makes it possible to aeroelastically tailor the wings and canards. They bend and twist in flight to the most favorable shape to give the aircraft increased transonic maneuverability and performance.
The Advanced Fighter Technology Integration F-16 program. The unconventional maneuvers of decoupled flight were evaluated. Vertical translation, lateral translation, pitch pointing, yaw pointing, and the maneuver that proved most effective for combat, flat turn.
The United States Department of Defense wanted to create a fighter plane that would be more agile. Stable design gave way to maneuverability.
This latest X program explores several different yet integrated technologies in one demonstrator aircraft.
Slow speed half maneuvers where the X-1 would most probably outperform current frontline fighters. Literally hundreds of feet is the radius of turn, which is very impressive.
A certain barrier exists for every flying vehicle. It is a barrier that has taken more lives than the erroneously named sound barrier. It is the stall, or high angle of attack, barrier.
The tendency of an aircraft to stall and become uncontrollable at slow speeds was the greatest limiting factor in an airplane's maneuverability.
High alpha, or high angle of attack, is the position of the aircraft's body and wings in relation to its actual flight path.
The benefit to a fighter airplane of being able to maneuver at high angles of attack is that it has the ability to put its weapons on a target, point and shoot.
The trouble has been that with the plane's nose pitched up at these high angles, it continues to fly in its original direction. This reduces lift, and when there's no lift, there's no control. Engineers place special movable paddle-like vanes near the engine's exhaust. These can be deflected into the exhaust flow to produce both pitch and yaw movements.
Nobody had flown a thrust vectoring airplane closed loop control yet. We flew the airplane to 117 degrees angle of attack.
The nose strakes allow selective triggering of the two hidden vortices which come off the nose. We can interrupt the flow of one and let the other one be still, generating more lift on one side and allowing us to turn the airplane.
I believe it will be married with micro machine technology and smart skin someday to control an airplane in more bird-like flight. Major leap in understanding and design. We really set the stage to assist in F-22, F-35.
To maintain the advantage in the air, close-in aerial combat beyond the normal flight envelope parameters is necessary.
The capabilities of this aircraft to decelerate in high angles of attack and to roll its nose around the velocity vector and flight path for pointing and weapons employment.
If in fact we succeed, we will have demonstrated a new way to fly.
Simply put, the X-31 allows the pilot to fly controllably well beyond that point where normal airplanes have their wings stall out.
The X-31s are conducting air-to-air engagements against a conventional jet fighter.
What you will see is the decoupling of the aircraft longitudinal axis from the velocity vector at high angles of attack.
This maneuver results in a very high turn rate and a very low turn radius, and is one of the fundamental advantages of post-stall maneuvering.
Seeing it was jaw-dropping.
An airplane is not supposed to do what the X-31 did. It's awesome. It was literally awesome.
The active program began to achieve flight research milestones, first ever supersonic pitch and yaw vectoring flights.
The nozzles themselves will vector the thrust plus or minus 20 degrees, about 4,000 pounds of load each in any direction at a high rate, about 80 degrees per second.
The X-36 is a remotely piloted research aircraft developed to demonstrate the maneuvering capability of a tailless fighter.
The maneuver capabilities of conventional aircraft are also limited by the pilot's physiological tolerances, such as the ability to withstand G-forces. Pilotless aircraft could be smaller, lighter, and more agile. With over a mile of lateral separation, they autonomously maneuver to preserve their configuration.
It's down about 10 degrees relative to the rest of the wing, but it allowed the airplane to be maneuvered quite aggressively compared to the way it was before.
What is it that gives birds their dexterity in the air? The best minds in aerospace have long dreamed of an airplane that can change its features and its structures and can soar like an eagle.
At high speeds on high-performance aircraft, all wings bend and twist. What we're trying to do is essentially control that wing aeroelastic twist, and by doing so, we're able to improve the maneuverability of the airplane.
Nobody has figured out how to make flying wings work. I mean, we see them every day, right? Birds. So now when you roll, you get yaw in the correct direction, in the same direction that you're rolling. We now have about 90 minutes of data that proves this works.